and we'll talk about neural networks today. So really get into the core topics. So last time, let's see what a little bit weird. Okay, one more thing. I guess okay, and also for this first day, it's not just you need to submit the homework, right? You need to submit your presentation preference by the end of the. Oh, sorry, I have a typo. It's not this class. By the end of this first day. So please submit your presentation preference. And I have a secret formula here to kind of sort the things out. As I mentioned, I don't want you guys to kind of present the same package. I mean, all 10 guys presenting the same package. So therefore, I will try to kind of I will try to have a function like that. I will try to minimize the cost. So, of course, if you have if your first priority is chosen, then there will be no cost for you. Otherwise, there will be some additional cost for that. And also, I would prefer, as many package cover as possible. So, wait a sec. So anyway, I don't think we need to get into this. So anyway, please just submit your presentation preference this Thursday. And and also I'll prioritize, as I mentioned, the most popular package will be presented first, and then if there's a tie, I will just break okay, anyway, if there's tie, I would do random breaking in any sense. So, okay, we will worry about that later on. So, another reminder again, please submit your homework by this Thursday, and also your package choice by this Thursday. And so last time we talked about basic concepts for regression and classification. To be more precise, we talk about actually last couple classes, we talk about regularization. Applied to linear regression. So we have rich regression, lasso, and so on. And we also look into linear classification. So and we have different loss function that will turn out to be let's say logistic regression. If you have binary classification, you have logistic regression, and if you have multi-class, you have a softmax classifier. And we also look into we introduce loss function and so on, again, maybe I should re-emphasize again, the whole point, the whole machine learning stuff is very simple. It's always you just introduce this loss function, and then for your training data, you just want to minimize your loss function, and sometimes you want to doesn't want your parameters to go really wild, and then you have this regularization constraint also added to the loss function. And then after you kind of define your loss function, it's always just a optimization problem. So we mentioned last time we can do simple stochastic gradient descent with mini batch, and also we can introduce momentum for that to kind of smooth out your optimization a little bit, make it more robust. And so we also mentioned we can visualize or interpret SVM, support vector machine, just as a linear classifier with hinge loss. And and one thing I just want to make a small correction last time. Actually, I also aware of that last time, but I didn't really go into much detail. But I have a sign problem last time that if I have hinge loss, basically the hinge loss is also sometimes you call it value function in another context. Is this function basically you will have when it's negative it's 0 and it's positive, then it's equal to the original value. So, but in any case, like, we want to make sure that the loss should be whenever this constraint. So remember that we have this SVM problem. We want to make the SVM. The hard margin. The hard margin in the sense that, like, okay, we have two classes, basically training samples. Like, these have different labels. This label +1, this label -1, and want to maximize this gap, right? So if we have a hard margin SVM, basically in this gap there will be no data points there. So if we say this is soft margin, we allow some data point there, but as long as, like, they are outside, then there should be no loss, right? So that will be captured by the fact that when it's outside, then this constraint will be satisfied. So therefore, like, 1 minus this guy negative, this guy will be negative. So therefore, if you look at this hinge loss, H function of this guy will be 0. So otherwise, it will be just equal to these things. So it will be just equal to, like, how far from this gap there, more or less. And I have the same typo there also for multi-class SVM. Also, like, instead of, like, SL x minus SJ, I should be, like, flip it. So it's just a minor correction of a minor typo last time. So any questions here? Tosa, also any questions? Like, you can press button if you want. Okay, so at least you guys have response, so I guess you can hear me. So if no questions, like, we just move on. So yes, so today we will talk about neural networks, as I mentioned. So we'll start with a review again. Like we mentioned perceptron not last time, maybe in the first lecture or two. So perceptron is basically just an artificial neuron, a very simple artificial neuron. So it's really a just the same linear classifier as what we have. So we have basically, again, we have inputs will be we will just sum all this input, weighted sum the input to get some output, and we go for activation function. And for perceptron, this activation function will be just a step function. So it will be either, if you're bigger than certain values, it will be 1, less than certain values, certain threshold will be 0. And according to Hinton, actually I have a link here. That's the message I got from his Coursera class. I cannot verify that, but at least he says so. So I believe it's true. So he said, like, this perceptrons is still used in industry, like when you have really a large number of parameters, like million number of features. So but other than that, like, it's not widely used. Actually, it's surprising to me it's still used. It's not surprising that it's not to be used, because it's not very easy to train a perceptron. Because, like, basically the main problem is, like, this step function is, like, not it's not differentiable. As you see, like, all the training the trick for training this neural network, all boils down, you do some back-propagation. It's just a kind of like, actually it's just simple calculus. You write it in a way that you can back-propagate back some derivative to correct to modify your parameters. But since your derivative here, like, is not defined, then it's basically the system will be broken, so you cannot use back-propagation. And if you really want to use perceptron, one thing is, like, you need to make the features to be separable. So therefore, like, in the past, when people use this kind of, like, system, they will first, like, hand code their features. So they have some, have an image, and then they just generate some feature for that image, maybe do some edge detection, some corner detection, and so on, and put those in as input features. And And it was the main area of actually research in many machine learning applications. Basically, just like have different machine learning applications, your perceptron or like your support vector machine is not going to change. The research in the past used to be like, okay, for different problems, we just hand code different features. We look at different problems, just guess like what kind of feature is good. Okay, we figure out, okay, this feature is good, and we plug into SVM or plug into Perceptron and train it, and then hopefully we get good results. And the main thing of deep learning or neural network that is getting so attractive is that like theoretically we can do end-to-end. I shouldn't say theoretically. In practice, many problems now we just do end-to-end. So we have input coming in, we don't care, we don't process it at all, like just an image coming in, and we have, at the end, we just, let's say, do a recognition saying, okay, this image is a tiger or like is an elephant. And we didn't do any hand code feature at the beginning. Then we just trained the whole system and with our training data. And actually somehow, if you look into the early layers, you can interpret the early layer just they're doing some automatic feature extraction for you. And okay, so and that's all for perceptron. And I guess I think I showed these slides before, but just to remind you guys. So some nomenclature for some architecture, neural network architectures. So we say like when we have one hidden layer, we say that's a two-layer neural network. So we have input layers, and then like we have one hidden layer, output layers. We call it two layers, and if like each nuance is connected to all nuance in the next layers, then will be called fully connected layers. And in the same manner, we can have like more layers, like 3 layers, 4 layers, and that's how the deep learning things come. I mean, why we call it deep. So, just a remark, again, I guess mentioned it before, just don't, of course, like the whole neural network thing is kind of, inspired by, biological neurons, but, it's really a very much simplified model. You can go for reference here. As a reference, actually this slide is kind of like, I borrowed it from CS231N, and biological neurons are very much different from the simplified model we have here. So we first of all, we have many different types, and the hydra there is really perform some very complex nonlinear operations, not like it's just like some linear add together and so on. And also like it has a time axis there, so it's really a dynamical system. So it's a nonlinear dynamical system. It's not really just at one time we sample it and do some addition. So it's just, I mean, I think should mention that because, some neurologists will be very unhappy. Like people always talk about this thing and like try to kind of, say, oh yeah, we're doing the same thing like this. But actually it's very different from what they do. Okay, the main focus today is going to talk about back-propagation. It's the classic algorithm that basically revived the neural networks area in 80s. Actually, it can be very easily understood. I took a neural network class like when I was a graduate student, and they have complicated formulas like just derive like back-propagation algorithm for these 2 layers neural networks. But if you kind of like visualize the neural networks more generically as so-called computational graph, then actually the back-propagation algorithm, as I mentioned earlier, is nothing but it's just propagating your derivative, like doing a chain rule for basically like computing your derivative using chain rule in calculus. So Okay, yes. Don't forget that like what we are always doing is just basically we want to tune the weight, right? So therefore like we want to find the partial derivative of the weight with respect to the loss function for each weight, basically each weight in each layer. And so I'll mention again, like back-propagation is just chain rule, nothing. It's really just chain rule. So so we'll look into computational graph, like look at several examples. I mean, computational graph you can imagine is like even a more generalized interpretation than neural networks, because in a computational graph, you can it doesn't need to be always like some neurons add together and then an activation function. You can have different operation. For example, you can have a max operation there. So from here on, I can't bore crazily from the CS231N from their slides. They did a really great job, so I just use their slides here. So here's an example that actually we given like earlier. That's a support vector machine that you can think of like support vector machine is just you have a linear kind of operation of the input. So basically you just multiply x by some weights there, a weight matrix, then you got some score, and then we compute the hinge loss, right? And you can also impose some regularization there, so regularize over the weight, and then you add together, you have the overall loss, and that's your loss function there. And actually you can go pretty crazy. For example, you have this Alex select here. It's actually already pretty early work, like back to 2012, have many complicated layers, but still you can kind of just imagine one layer or one operation at a time, just stack together with each node basically is just an operation to the input, and then kind of send out some output. So give a very simple example here. So let's say I have a x, y, and z here. So I have basically fx, y, z is equal to this guy here. So let's say you can imagine, for example, this can be some loss here, right? So it can be a loss, and you want to compute derivative over x, y, and z. So maybe some of them are weights, some of them are input. But here it doesn't matter. We just, let's say we want to compute the derivative for all of them. So and let's say we have the input here. Inputs are x equal to -2, y equal to 5, and z equal to -4. Then in the forward pass, you just go through this computational graph, right? So I have this x plus y multiplied by z. I can written like this way. So I first x plus y, I have a plus operator. I spell this guy. So -2 plus 5, I get 3 here. Then this multiplied with z. So I guess -12 here. So here I call it f, let's say. So yeah, here's f. Then look at the partial derivative. So I have q is equal to x plus y, right? So I have intermediate random variable here, q, intermediate variable, q here is equal to x plus y, and f is like q multiplied by z. Then so if you look at just like for each node, the partial derivative of the output with respect to the input. So for example, this guy q partial derivative of q with respect to x will be equal to 1. Okay, this is equal to 1. And this guy, I want to see the partial derivative with respect to q and z. So I got this here. So, and again, I want to compute these three guys here. So I have the forward pass that compute this, and at the same time, actually, I should compute the derivative of I should compute this partial derivative along the way also. For example, like here when I pass this -2 and 5 to this guy here, in the forward pass, I can immediately also compute the partial derivative of q with respect to x and y. So in that case, it's very simple, just 1 and 1 here. Here, in practice, is actually will store like both this value of 3 and also this partial derivative 1 and 1. So we store somewhere here. It's not showing here, but yeah, it was supposed to store here. So then in this pass also, it passed to here. It will compute, of course, this f here, but also the partial derivative of where f with respect to this input q and z. So I will compute basically partial f with respect to q, that's just equal to z, right? So z is -4, therefore I will store -4 there, and this is equal to q, I will store like 3 here, something like. So then when I want to compute all the partial derivative for this guy, then I will go backward. First I have a trivial kind of derivative, basically partial f is just equal to 1. And then like this guy now, I know that this will be equal to partial f, partial z, right? So it's trivial, but yeah, you can imagine like that. So I compute partial f, partial z in the forward pass, right? Because this is one of the input of this guy here. So therefore I can just multiply this 1 with this guy here. So earlier this, let's see, go back. I have -4, 3, right? I can multiply, I think it's this guy probably. I can multiply this -4 with, sorry, I think it's 3 here. 3 with this 1 here, so I get 3 here. And the same, for the same token, for this guy, I can also like multiply 1 by this -4 here. So therefore I got this -4 back here. So then remember also like this guy here, I have the partial derivative for q with respect to this input and input. So I have a 1, 1 here also. So, and then I want to compute partial derivative of this guy with respect to okay, I want to compute partial L, partial X, right? But this should be equal to partial L, partial Q, and partial Q, partial X, right? And partial L, partial Q is found in the previous step, right? Remember, like when I pass through here, I compute this partial L, partial Q here. That is equal to -4 here. And then this partial L, partial X, therefore, will be equal to this partial L, partial Q. Let me write it better. This guy, that's -4, multiplied by this partial Q, partial X is equal to 1 multiplied by 1. Therefore, like I'll pop back like -4, and then like this guy pop back -4. So it's very simple, basically. So I can go for a couple more examples, but the key idea is like this, right? So for each node, when in the forward pass, you have some input coming in, right? Input coming in, you know what is the output. You can just, okay, this output is just equal to f, x, y, right? And at the same time, you want to compute also the partial derivative of f, partial derivative of f with respect to input x, and partial derivative of f with input y. And then, yeah, this f is z here. So anyway, so then when it go back, then you will basically consume this kind of like partial derivative. So therefore, like one thing is interesting that like in practical implementation, one thing need to consider when you have forward pass, you store lots of values. Basically, you store the output of each of the node, and also you will store the partial derivative of this output with respect to each of the inputs. So for example, here you will store 3 values here, and when you go back, you will basically consume these partial derivatives. Or yeah, this one kind of intermediate, you don't need to store it, but this guy you need to store it in the forward pass. When you go back, like you need to, then you consume this guy. So when you want or ever do practical kind of like look at some framework, and if you check the memory, you see that when it went forward, then it just consume all the memory, and when it go backward, it's just like, okay, the memory got released. So yeah, then yeah, here is a very simple way. It's a chain. It's nothing. So any questions? So I can go for one other, like a little bit more. Okay, it's still like very simple example, right? So for example, I have a little bit more complicated function here, but still I can just decompose it into like multiple this kind of operations, right? I can say I have this W0, X0, W1, X1, W2 here. Sorry, the font is so small, I'm not sure that you guys can read it. So this so then this will be basically W0 multiplied by X0, so it's this guy here, and this is W1 multiplied by X1, and then this will be this add with this will be W0 X0 add with W1 X1, and I add this guy as at W2 here, that will be W0 X0 W1 X1 at W2, and so on and so forth. And then I can have one operation just do a multiply by -1, one operation just do exponential, and then one operation +1, and so on and so forth. And I have this final operation just take an inverse of x. So again, like this, I already have these values for the forward pass. So let's say this is the input values there. So when I go along the nodes, I will compute all these kind of outputs, right? And at the same time here, I'm not showing that, but it also compute the partial derivative of the output with respect to the inputs. So then I have all these partial derivatives here. Yeah, it's okay. I mean, but as long as you get the idea. So for example, here, at the end here, I have this x is equal to this. At this point here, the input is 1.37, and taking the inverse is 0.73. And I take the partial derivative of this guy is like -1 over x squared, right? So I have some values should be equal to what? 1 over my -1 over 1.37 squared, something like that. So that's the local partial derivative for this guy. So when I go backward, like starting from here, I can at the very end I have a trivial derivative here is just partial f is equal to 1, and the partial derivative of f with respect to this variable here will be just equal to partial f multiplied by this partial x, if I call this x. So then it will be just equal to, yeah, like here it will be just equal to -0.53. Then I can continue to go back, and this guy just add 1. Add 1 will be the derivative just 1, right? So I will have 1 multiplied by this guy, right? So this exponential, the derivative will be exponential also, right? Exponential the input, right? So it will be like exponential -1 should be. So therefore I have exponential -1 multiplied by this guy here. Then I keep going backwards, so I have the derivative now is like -0.02, and then this guy is just multiply -1, then I have should multiply by -1, right? The derivative at this local derivative is -1. And for this guy, so I have two of them. Like in the forward pass, I should have store already like two partial derivative for these two inputs. Of course, this is just addition. I mean, the derivative is very simple. It's just should be just equal to 1. So therefore, like it's just this is 0.2. So I have this, both of them will be just 0.2. And then again, I have plus sign here. Again, this just pass the derivative here just 1. So it's like 0.2 again. And then this, yeah, I have this derivative of this output with respect to this guy, and this guy will be equal to equal to 2 and -1. And so anyway, any questions really? I mean, like I think like the idea is very simple. And as long as you grasp the idea of computational graph, That's why it's okay. Like you're pretty rusty with calculus. I mean, like you can split into very tiny function, right? And then you check the table if you don't really remember that, or you just use mathematical or like MATLAB or something like that. And even more, like yes.
So let's proceed. We just have the first thing is to look at the partial noise in the most direction. So in this example,
Yes.
we need to noise the partial in the most direction. And the final procedure is calculated in the most left.
I guess the question is the procedure. Is that like how does it? It should first go through the forward pass.
The first thing we need to do is to look at the lowest partial in the most right.
The derivative is that you mean the derivative?
Yes.
Yes, the derivative will be yes. So when you compute the values, you will go like this way. Okay, you compute the input, compute the output for each of the node there. But at the same time, you also compute the partial derivative. But the partial derivative is I would say the local partial derivative. That means that, like for example, for this particular node, it's just the partial derivative of output of this node with respect to the input of this node. So these two and you will store them. You will basically store them like for each of these. I mean, store locally, like at each node, maybe. Like you can imagine how they implement. They have many ways to implement that, but one way maybe you have each node is like a structure, and then you store the partial derivative in that structure. And then, after you have the forward pass, when you compute the partial derivative of basically the final output with respect to all the intermediate values. So you basically will eventually you compute the partial derivative of this output with respect to everything here. This one, and all this output here. Then you will basically go backward one at a time. And it will be simply equal to starting with 1 multiplied by the local derivative for this node. So for example, the local derivative for this node is just equal to minus 1 over x squared, right? So it's just equal to minus 1 over 0.53, something like that. And then you multiply by 1, so you get back like minus 0.53. And then you continue to go back. So therefore they call it back propagation, yes.
I think it's just like the last one, this complicated this time. Because we don't change anything in the green parameter. So the green parameter we need to change it and to get a good result. So if we plus 1 and the green parameter doesn't change.
You mean the plus 1 here? Plus 1 minus 1, something like that?
In the right.
This one? Oh, yeah.
So the value didn't change.
You mean the derivative doesn't change? The value will change, right? Because you add 1. So okay, yes.
I mean, can we just pass the plus 1 because the result didn't change?
I guess I'm not sure the next time I answer your question. It's like, you can definitely, if you think it's not efficient to pay one at a time, you can absorb some of these nodes, right? For example, like, you realize, okay, this whole function is just a sigmoid function, right? So this is equal to 1 over 1 plus exponential minus x. If you have an x here, input, the output is just equal to that. So you can just, sometimes you can just put everything together. Then and then as long as you are happy computing the local derivative of this guy, right? And if you think, okay, it's too complicated, then you can split into smaller steps, right? So, I'm not sure I answer your question because, yeah.
When you go this way, derivative plus 1 is 0. Plus 1 is not affected. Oh.
Can you repeat the question, basically?
Yeah, just in the
yes.
Yeah.
Yeah.
Just based on time.
Oh, okay, yeah. I hope like this slide answer your question. Actually, you can, if you don't like that, okay, I want to be quicker. Actually, you can just put things together. So as long as you can print the whole thing as one big block, right? So, and then you will compute the derivative immediately. Let's say, okay, I assume this all combined into one big thing. So you think of one function, right? As long as you know how to compute the derivative from the, basically from the output to the input for this guy, right? So, but if you want to, okay, I'm kind of rusty with my calculus and algebra, I want to make things simple, so I can always split into like decompose it into very simple components and tackle them. Yeah, but it's really just a matter of taste. Yeah, so and of course, like, yeah, if you put things together, it will be more efficient and saves memories, because you know that like each time you store, like for each of the nodes, you need to store the kind of the partial derivative of the output of the node with respect to the inputs, right? So yeah, it's true that like if you put things together, you get use less space and probably will be faster and so on. But also like there's always trade-off. It's like you write, like whether you want to write assembly language or like write C or like write Python. Maybe you want to get high level and make things simple. You don't want to deal with like the calculus yourself. Maybe then you can split into like easier components. Okay, that's just kind of a, I guess, a small quiz for you guys. Like, so I have add gates there. So actually it's not exactly. So the actually it has the answer here. It's not a good quiz. So but if you think of like the addition and multiplication and so on, the derivative for the addition will be, okay, you know that like it'll be just like okay, if I have like x plus y, then if partial derivative this z with respect to x, I'll just equal to 1, right? So therefore, like it's basically just like a gradient distributor. If you backpop back the derivative, you just like distribute like your derivative like to your inputs. And okay, how about max gate? So if I have max, operation. Actually, I have to kind of answer here also. Or like I have to. So you can see that like if I have the derivative here, it will go to one of these guys, right? So basically, like it's like a router. So you can think of like you have like many inputs. They only go to one of the inputs. Basically, go to the maximum values there. So yeah. So you have like 10 values, and that go for the max operator, and then it goes to something else. When you backpop back a derivative, it will just go to one of the inputs. Basically, it will go to the input that is maximum. And of course, minimum will be just the opposite. It will go to the input that is minimum. And how about multiplication, like this guy here? That second one? This one or? Yes, this gate. Actually, yes, I guess you get the idea. So, actually, it's kind of, I'm not as good naming for that. It's kind of like a switcher in the sense that, like, if you have like a derivative coming here, like, going back, so then, you have input like here is like 3, here input is like -4. You backpop to this guy by multiplying the input from this side. Yeah, and you backprop to this guy by multiplying to input from this side. So it's like this. Therefore, derivative for this guy, like with respect to this guy, will be equal to 2 multiplied by 3. So of course you can write it down, or like most of the time you don't even need to know it because the framework will automatically compute for you. So anyway. So but that's backprop. One thing I didn't mention though is like if we didn't have example have more than one output, right? We only have the examples we gave always only have like each node only have one output. But if we have multiple outputs, then the derivative going back will be just add them together. If you think of that, it's basically still a chain rule, right? So if let's say I have let's see how I can let's say I eventually have this is like x1, x2, and I have like partial derivative with eventually with respect to some guy like why I pick x1, I guess better pick y1, y2 maybe, and x, let's say. Then I have this final f with respect to x will be like partial f, partial y1, partial f, partial y1, partial x, plus partial f, partial y2, plus partial, partial y2, partial x, right? So therefore, like you basically you need to add. So yeah, this will be the derivative like from this guy, right? And add derivative from this guy, and of course, a partial y1, partial x, and partial y2, partial x is the same thing because the output, supposing your output is the same output. Should I? Yeah, I think so. Like, otherwise I can just write like this, right? I assume like, if this actually two outputs are different, then actually this is basically two different nodes, right? So here I'm really, these two outputs supposed to be the same, otherwise I can just draw two outputs. So anyway, if you get confused, just go back home and draw it, then you'll get convinced yourself. So, but if not, you can also just trust me. It's just add them together, basically. So, last thing we didn't mention though is like, we assume all these input and outputs are scalar. So, what if they are vector variables? So, then in that case it will be, okay, if you remember matrix algebra and so on, you can just go for like Jacobian and so on and so forth. So then you compute Jacobian somehow, will be like, when we backprop, will be like, having, the derivative here, partial L, partial Z, multiplied by this is basically like a Jacobian somehow. And, so what I want to say, it would be kind of complicated because it would be a matrix. But in practice, it's not as bad as it looks here. Because if you think of element-wise, as I will give you in an example, okay, before an example, you see like if I do it like just think of it really a matrix. Then the matrix itself, for example, if I have like, this like 4096 input and 4096 output, then the matrix size will be like 4096 multiplied 4096, right? It's pretty big. And also remember, like, for each input, like, you have different output. For each input, like, you have a different Jacobian matrix. So, therefore, like, if you have, like, let's say for a batch, of training data, let's say, like, just a mini batch with 100 data samples, then you will have, like, 100 so many matrices. So, it will quickly become, like, pretty big. So vector-wise, the things like blindly actually is not a good idea in this case. Because most of the time actually we don't need that. Because let's look at this simple example. Let's say I have, again, I have this, just computing the absolute values, or like the second norm of a vector multiplied by some weighted matrix like W. So I have this is a matrix and this is a vector, something like. And I can draw like this, right? So as earlier, so I can think of, okay, this is multiplication, and then I compute the L2 norm. So although like this multiplication is not scalar multiplication as earlier, so it's a matrix multiplication. Now think of something more concrete. Let's say I have W is 2 by 2 and the X itself is 2 by 1. And then I will have, okay, and let's say I call here is Q is equal to this guy here, and then that of course like this Q should be like 2 by 1 also, should have like some Q1 Q2, so this multiplied by this I just get a vector of length 2. So I compare L2 norm, I should just get a scalar value here. So it will be something like that. So now if I backprop, then okay, actually when I do the forward computation, I forgot to mention, remember that we need to compute the local derivative of the output of a node with respect to all its inputs, right? So for example, like for this guy, when I compute this guy, I should also compute the partial derivative of this output with respect to like W and also X. So if you think of like earlier slides where we talk about like the dimension of the input actually is 6, right? I have 6 different, I can imagine there's 6 different scalar variables here, right? So, and therefore like the Jacobian like, should be like, have a dimension of like, 6 by 6 or like 36, right? And I have 2 outputs. Actually, I should have like 72 variables there if I compute all of them. But actually, many of them turns out will be equal to 0. I don't really need that because I can just, okay, if I just compute, let's say, the partial derivative of this output with respect to W here. Okay, I should maybe, okay, that's here with respect to W. Actually, I can argue that that should be only 4 values. And I know that it should be only 4 values because like for each of the parameters that should have a derivative there, right? So therefore that's each of these values actually correspond to the derivative of the output with respect to each of these values here. And I seems to make a mistake though, I'm thinking. Let's see, if I for this node here, if I compute the partial derivative at this node, it seems I need to store, for this guy, I need to store 8 values, right? Because I have, No, that's no 8 values. Yeah, 4 values is correct. So if I, let's see if I have it here. Yeah, so, yeah, here, for this guy here, so, partial derivative of this guy with respect to W, should be very simple, right? If you think of that, because I can write it down, right? What I have this Q here, is simply, I have the Q. Basically, let me just write like this first. Q1, Q2 is equal to W multiplied by X here, and and this is basically equal to something like W11, W12, W21, W22 times X1, X2, right? So therefore, like if I want to find the output with respect to the input, like for example, if I want to find like partial Q1 with respect to partial W11, then Q1 is equal to what? W11 multiplied by X1 plus W12 multiplied by X2, right? So therefore, it's just equal to what? Just equal to X1, right? I mean, this is just equal to W11 X1 plus W2, and this W21 X1 plus W2. And similarly, if I have like partial Q1, let's say, also partial like W21, then actually Q1 does not depend on 21, right? This is 21 here, and this is Q1, this is Q2. So this should be equal to 0, right? So what I get is basically we have something like this here. It's just equal to partial derivative Qk with respect to Wij will be just Xj. But also have an indicator function here. I need to make sure that k equal to I, otherwise it will be equal to 0. So then when I go back, okay, this actually have 8 values there. It's not ideal. There's 8 values there, and if I implement that kind of brute force or like blindly, then I guess I really need to store 8 values there. And this have for this guy I need to store 4 values there. So there will be kind of 12 values there, but still it's much better than if I do it brute force. I consider all these variables are variables and compute the Jacobian, then I will have like 36 variables or like 72, depends on how you count it. So anyway, I mean like but it basically is still the same idea as before. It seems to me I'm just make things more confusing than I kind of trying to help. But if I did confuse you guys, I just remember like we are basically doing exactly the same thing as before. But just when we have this vector input like matrix input like or like matrix output, then you just make sure that you need to take partial derivative of this output with respect to these guys here carefully. And actually there's a remark here. It's pretty nice. You remember that when you go back, the derivative, the size of the derivatives should be the same as your input. Yeah. So and we can do the same for here. We've got something like this. Any questions here? I guess I guess make it a little bit.
Alright, so
Yes.
it looks
Yeah.
like so you have the formula at the bottom that was.
Yes.
Can you go back a second?
Yes, yes, yes.
Yeah. So you're saying df, dw, ij, which is that partial that you're trying to calculate. That's the matrix on the far left.
Yes,
right?
yes.
You're saying that that's equal to 2qi times xj. So that kind of makes sense. Like if you have 0.44, you multiply that by 2, right, and then you get 0.88, and you're saying you multiply that by 0.1, which would be the x.
Oh, sorry, I get lost. Like, which one you're talking about? This here or like this here?
So at the very end, you have,
Yes, here.
after you do all your simplification, you have 2qi
Yes,
times xj.
Yes.
Yeah. So like if we just actually do that on the first one there, the qi would be 0.44, right?
QI is
Back-propagating across the
0.44.
matrix multiplication.
Actually, QI should be 0.22. Wait, QI is the output. So QI is actually 0.22 and 0.26 because it's a vector.
Okay.
Yeah.
Okay. And
Yeah.
then
So this is the
x-
derivative. Yes.
So so q would be the green one, the 0.22 and the 0.26.
Yes.
And then what is x?
X is this here. So
Okay, so that's the other matrix.
yes.
Okay.
Yes.
Got it.
This one here is actually partial derivative of this output. I don't know what do we call it. Let's call it F with respect to Q. Yeah, Q1 and Q2.
Right.
Yes.
Yeah. Okay. Yeah. No, that
Yeah.
makes sense.
Yeah. So luckily, I think like even for vector variables, most likely you don't. I believe packages will handle that. I'm not 100% sure, but you guys will figure that out. Remember, like, okay, I for guys that came in late, like, remember you guys supposed to hand in homework and also like, send me the presentation preference, like by this first day. So, okay, that's okay. Finally, just give some rough pseudocode of like how you eventually going to implement that. So let's say you have create a structure, a class for that, then maybe you have some forward function and backward function. Exactly what I said, like forward function, which basically you compute the values and also compute the local derivative, and backward just kind of like back-propagate the derivative, multiply with the local derivative. So this is an example. Let's say I have x multiplied by y equal to z, and I have forward, I have something like that, and let's see, the next slide probably is better. Then the derivative, like remember, like if I have x multiplied by y, then one of the derivative will be y, while one of the derivative will be x. So I also keep the local derivative. So I'm not sure this is a good. Probably like should shift. Self x is equal to x, self y is equal to y. So and then like when you backward, then you just absorb this local derivative, right? So you remember, okay, the local derivative here is self y and self x, and then you multiply with this back-propagated derivative and get this derivative back. And I suppose one of the homework you're going to implement something like that. So I probably hand it out pretty soon after you submit the first one. So some remark again, like actually we already mentioned that, like, so forward pass, like we basically compute local derivative and also the output, and backward pass you consume all these local derivatives, and therefore, like as mentioned earlier, like you will see actually a large spike of memory consumption, like when you do the forward pass, and so if you survive forward pass, then your hardware probably is kind of like have enough memory. Otherwise, you just need to scale down your model. Maybe have like the batch size is smaller, and then you won't have like memory issues. And of course, like up to now we only talked about like how to compute the gradients, and sometimes people say, okay, they kind of train the model using backprop, but it's a little bit misnomer there, because like we also need to have other component to do the optimization. We just compute, okay, the gradient first, but then we need to see like how we're going to optimize. And actually we mentioned a little bit using the stochastic gradient descent, right? But we will talk more next time. I guess I will just stop here.